Okay, let's go ahead and get started. So a few announcements today. The first is that the Homework 1 solutions were released today, earlier by the TAs. Now there's a few odd things here that I want to call to mind. So we released the homeworks. They're only posted on Piazza, not on the course website, and they're released as images, not as actual text. So there's two reasons for that. The first one is that the code is fairly short, or at least our references are fairly short, and the thought is that if you want to go through it in detail, the best way to actually go through it is not just to copy and paste it, but to actually transcribe the code again. I'm actually a big believer in that. I've spent a lot of time transcribing code myself, or transcribing like math or things I have to go through. It seems like a waste of time, but it actually, I think, helps really solidify some of the ideas. So if you didn't quite get the full score and sort of are wondering why, I think it can be much more helpful to go through and retype what it is rather than just, and the temptation to copy and paste is just too great when you have the code in front of you. Last year, I think someone very helpfully OCR'd all the code and posted that on Piazza, which is not what we're going for. So please don't do that. But that's a philosophy we have. You know, I do sort of feel strongly about that. So that is what it is. The other thing is that, as you guys have probably sort of realized, and this is something I kind of fully admit, is that auto-graded assignments, especially ones that query the external web, are not that easy to sort of write the auto-graders for, right? So we do reuse large portions of the code each year, and there's that much less chance of it kind of getting out and spreading into the wild if we release it both as images and only on Piazza. So obviously, please do not distribute these solutions anywhere. It just makes everyone, you guys have benefited a lot from the fact that last year they were able to debug a lot of things. Believe it or not, it's actually going quite smoothly, the auto grading compared to last year. And so everyone benefits if we have sort of more well-versed solutions, which next year we're going to have even more well sort of tested solutions. So please don't post those anywhere, or it gets to the point where we have to start with a completely new problem set, and that I think, when it comes to auto-grading, there has some problems with that. Okay, so the next thing is that there's some confusion, I think, about this point on Piazza. So I've mentioned before that you need to tag posts on Piazza with the homework question. And what people are doing, a lot of people are doing, is that they're just writing the homework question in the title and then tagging it as homework 2. So don't do that. There's actually tags. I can even go and show people here. So when you create a new Piazza poll, I'll open it in a second. Okay, so when I create a new post here, if I were to do that, there's tags here for the actual sub-questions. So don't just write the title being the homework question and select homework 2. You can select homework 2 if you want, but then more importantly, select, is it the graph library problem, is it this problem, etc. If it really is genuinely not a problem that has any specific thing, that's fine, just tag it homework 2. But there are a lot of questions just tagged homework 2 with the title being the actual homework problem there is. So we're trying to get to those. We're not trying to avoid those, but just in the aim of helping other people looking at Piazza, try to tag it with the actual sub-question, where these things here are what I mean by the tags. Okay, actually let me put this back. Okay. Let's see, I want to go back actually. Okay. All right, the second thing is that there is one sort of weird issue with this particular homework 2 now in the auto grading. Because we're grading files that use matplotlib, so we import matplotlib in our grading script. When matplotlib is run for the first time in a VM, it pops up this message saying there's like a font caching thing. Because it's a warning, it will actually show in the autograder no matter what. And so a lot of people are thinking that is their error. Their error is something related to matplotlib. I agree this is actually a bug in the grader, by the way. It should not show that error if it's not the actual problem. Matplotlib is never actually the problem. What's happening is that the code is just timing out. So the notebooks are timing out. It's in the time limit. And that's causing it to show the last error that it showed, which is this matplotlib error. So it has nothing to do with matplotlib. It's not even probably the notebook you're thinking of that uses matplotlib. It's actually just the fact that one of your notebooks is timing out, taking more than the allotted time, and so that's causing the error there. So that's nothing to do with matplotlib. We're trying to address this to fix this so it doesn't report it as such, but just for now, know that it's not actually matplotlib causing the error. And the last thing, and this is something that hopefully I'll be able to do this, but I think I'll try to be a little bit more prompt on the note updates this week. I got a little bit behind on some of the notes, just posting now the graph ones that just posted before class, but some of the graph ones up to the last lectures for the worth of graph ones. But I think at least by next week, we'll say, I should be on the ideal schedule of posting them before class, but we'll see how that actually works out in practice. Okay, so let me, any questions about any of these top points here? Okay, let me then jump to last lecture, which is our lectures on, we were just getting to talking about PageRank last time. So today we're actually going to cover both, finish up talking about graphs and then get to at least the start of free text analysis. We're not going to finish that, and actually there's some more material that I'm going to add for Wednesday, but we're going to hopefully get that, and then probably the overflow lecture will cover the geographic information systems in the end. So let me get started then with PageRank. So remember we talked about PageRank, kind of motivating it in terms of finding important nodes in a network, right? And this is the algorithm, of course, that started at Google. Google wanted to know what search results to show, and you're going to show search results. It's a good idea to show important pages as your search results, at least amongst the ones that all, say, match the search term that user inputs. And so the PageRank process is the following. It sort of simulates this following process. Someone who is kind of randomly clicking on links on the web. They start at some random node on the web, a page on the web. They click randomly to some link in that page. And if the node has no outgoing links, they just jump to a new random page. And they optionally maybe also jump to some new random page with probability D. So this is just a definition of sort of the process by which, an imaginary user, not a very interesting one, browses the web. And the idea is their notion, PageRank's notion of importance is the probability that you're going to wind up when following this process at a given node. That is just sort of how they define probability here. And we'll see what that actually kind of means in a second in terms of different graphs, in terms of at least a simple graph. And of course, in the homework, you'll deal with a much more involved graph in the 688 question. Okay, so I'm going to sort of define the PageRank algorithm right now. And I want to highlight a few. I'm going to kind of describe it mathematically, but I want to highlight a few points which we also kind of describe in the homework some. I'll have to leave a little bit of it ambiguous because some of it actually is part of the homework. So you start off by initializing A to be the adjacent. So you're given some graph G, and we want to compute the importance, the PageRank score of all the nodes in this graph. You're going to first replace all the columns in P. Sorry, you're going to first form the adjacency matrix of the graph and store that in A. Then you're going to take A, and you're going to take any column in A, that has all 0 entries. Remember, in the adjacency matrix representation, the format was that a element in row I and column J means there was a link from node J to node I. So let me just write this here. I'm going to switch to this. I have to use this document cam or it doesn't work. But if A is some matrix here, wait, is that the right one? Do you know if that one's being captured or is that is that one? Use this one. Okay. Yeah. There was a problem with that last time, so I apologize to people in the video who that messed up. Okay. So if there's an entry here in the jth column and the ith row right here, this means that in the graph there's a link from node J to node I. In other words, there's a link on the web page J to the web page I. So what this means in PageRank is that if there are no entries in the jth column, that means that web page has no outgoing links. Okay? And so what we do in that case, this was just the definition of PageRank, is that we replace that with kind of all ones. And then we normalize the columns. We make them all, the columns have to sum to 1. They have to be probabilities. So we normalize them by dividing them by 1. Sorry, dividing them by their sum. Okay, and now we have this matrix P, and P is now a probability matrix, right? It actually encodes kind of a transition probabilities over this graph. It's what's actually called a random walk over the graph. We're basically taking random steps, and if there's, essentially if there's if there's 2 entries in our matrix, say one here and 1 here. Forget about this one for a second. Then what you would do is that after you normalize them, P would be equal to 1/2 and 1/2. And so being in that column would imply that you have a 1/2 probability of going to each of the 2 outgoing links that it has. All right, so you do this, and now you also construct sort of this p hat matrix. And this p hat matrix is 1 minus d equal to p. That's encoding the fact that with probability 1 minus d, you sort of follow this random walk dynamics. And with probability d, you jump to a random node. And the way you jump to a random node here is that we take this matrix here, which is 1 transpose divided by v, the number of nodes in the graph. That is a kind of all ones matrix normalized to have 1 over v in each entry. That's kind of like the random jump to any node probability matrix. And so with that probability, d times that probability, you end up jumping to a random node. Now we initialize x with a uniform distribution over all the nodes, just 1 over v times the vector of all ones. And then we just repeat this process. We just keep multiplying x by p. Now again, what this is doing is this is simulating the sort of random walk process over the graph. For those that sort of have heard these terms before, you may have heard these terms before, so if you haven't, don't really worry about it. But what we're setting up in some senses is what's called a Markov chain. It's sort of a simulation of what happens when you follow these probabilities here. And what we're actually doing is we're confining the stationary distribution of this Markov chain. We're actually finding sort of what happens if you run this forever, what distribution do you converge to? That incidentally also happens to be the largest, eigenvector corresponding to the largest eigenvalue of this matrix. But I've said that we aren't going to worry about matrices or anything beyond inverses for matrices. So don't worry about that at all. But if you have heard that before, just know that we are doing that. But really all that you can kind of think of this intuitively as is we are trying to essentially take, we start off with a uniform vector. That's jump to any web page at random. We simulate this process of kind of taking little steps on this graph. And at the end of enough time, we'll converge to some sort of distribution over what nodes we're likely to be in. This distribution, after we've repeated it a whole bunch of times, is in fact the PageRank score. So let's take a little example here, because I think this will be much more concrete with a quick example. Let's take our favorite graph now that we've been dealing with a lot. You will, in 688 at least, apply this to a much more interesting graph. We'll apply that to Wikipedia and see if you click on Wikipedia randomly, it's actually not that uncommon, I think, a browsing pattern from Wikipedia. If you clicked on Wikipedia links randomly, where would you end up in Wikipedia? So you'll see that in the homework. I think actually even the question says what it is, what you should be getting. But OK, so we have our graph here. And this is the adjacency matrix that's encoded by this graph. And we're going to run the PageRank algorithm with this d probability equal to 0.9. That's the probability that we stay. Did I write this wrong? D should be the probability that we. Sorry, I think I meant d to be here 0.1, not 0.9. Let me actually fix that. Right. The probability that we jump to a random point there is actually 0.1. With 0.9% probability, we sort of stick to the evolution as it should be. OK, so actually, who has an idea about, not looking at the notes here, who has an idea about what's the most important graph? Or sorry, what's the most important node in this graph? C. D? C? OK, C. I like C. It sort of seems like there's a little cycle here. You kind of go around, but somehow like you point more to there, maybe. Not sure, right? So let's see. Let's see what PageRank actually says. OK, so the first thing we do is we form this. We first replace the last column in A's with all ones, basically, and then we normalize them. So we divide their columns by the sum of the entries in that column, and that's the sum that we have. And that becomes now our probability transition matrix, essentially, is what it is, called P. Okay. So now we also take this and we augment it with probability 0.1, 0.9, we follow this. With probability 0.1, we follow a random transition matrix. That would be all the, actually 1/4 everywhere here in a big matrix. And then we take the weighted average there, and that's this matrix here. So this is our p hat matrix. And now we apply it to x repeatedly. And I won't do it. This will be in the notes momentarily. But when you do this, you get this as your probabilities. So in fact, you do have the fact that C is the most important matrix here. Does anyone want to sort of explain why that is? Why do you think that is? That's what it's true, but it's also kind of odd, right? Because it's maximum number of edges, but one of them's outgoing, right? Only one edge incoming. So why would that cause it to be there more frequently? Yeah. Yeah. So the way I sort of think about this is that if you go to D, you'll jump randomly to anywhere, right? And if you go to one of these other ones, you're definitely going to kind of hit C eventually, right? So C in some sense, even though it doesn't have more incoming edges, it still kind of is in more paths to get to things than anything else. But more than that, it just ends up being the highest probability there. So again, I think the real point I actually want to convey is that it's not at all obvious which is the most important node in this thing. I mean, you probably say C just because it has the most edges, but having the most edges when they're all outgoing wouldn't actually do very much for you. So it's actually not at all obvious what node is the most important here. And the same definitely goes for the web as a whole, right? And so this PageRank algorithm gives you one answer as to what nodes are important or not that seems to have worked very well in practice. I mean, it worked very well in terms of search results, and people sort of like those results. Yeah, there's one question there. Right, so p hat is 0.9 times this plus 0.1 times the all ones matrix divided by 4. So the all 0.25 matrix. That is this. So the all 0.25 matrix would be this term here. Without the D, right? Because it's 1, 1, that's all ones, divided by the number of nodes, that would be the all 0.25 times 0.1 plus 0.9 times that thing. And it's also a really yeah, there's a question there. Right, so the question is, how do you set the value of D? And that's a total just, how do you want your process to work, right? I forget what actually Google uses for the value of D. I think it's like 0.1 or something like that. Or I remember reading that, something like that somewhere. The reality is, so there are trade-offs involved, right? So if you think about a graph that has a set of web pages, right, that has a very long list of sort of one links after the other. So maybe you're stuck in like a novel or something like that, where there's only one link to go forward, right? If you have D equal to 0, then once you get to that first page, you always keep stepping to the next page. So you have nowhere to go, but just keep stepping and stepping like that. And it basically emphasizes the importance of the nodes far down in the chain. Because the things far in the chain are kind of as likely as things at the beginning of the chain, because once you hit the beginning of the chain, you always reach those nodes at the end. Adding D lets you sort of emphasize the fact that the nodes at the beginning, if they have incoming links from elsewhere, are probably a little bit more important than the nodes at the very end of the chain. So hopefully that made sense. I didn't really write it down, but basically, maybe I'll just do it here. If you have a long chain like this in your graph, if D is 0, and say there's a lot of edges pointing here, if D is 0, then this one will have the same importance as that one. Because whenever you enter this node, you'll always follow the chain to go there. If D is 0.1, this one will have less importance than that one, because you might at some point sort of skip to a random one here, and you're more likely to end up back there. So that's the sort of the motivation for having that D term that makes you want to use that instead of just always follow nodes kind of regardless. Yeah. So the question was, what if D is 0.9? So what if I hadn't made a typo and actually had did it like that in the slides? So if D is 0.9, as D gets to 1, all nodes get the same probability because you're just sort of jumping randomly every single time, right? So when D gets closer and closer to 1, you're basically following chains less and less. So this one would have almost no importance here because it's just, I mean, you're just going to jump, maybe one time, right? You probably, if you're here, you probably won't jump there. So all nodes kind of blend together and have the same amount of importance when D gets bigger and bigger. Yeah, maybe last one.
D in our graph points to itself.
What if D in the graph? So now you're talking about this D here, right? This D here, not little d. Yeah. What if D points to itself? In PageRank self-link, I believe you don't have self loops in PageRank. I mean, in the web, you don't have links to yourself. I guess you can, but doesn't really mean anything. So in general, yeah, you ignore self loops in PageRank.
Makes it self-important. It will only jump to itself.
Yeah, so that's actually a good question, right? So I think that there are these ways you can kind of trick PageRank, right? And actually, tricking PageRank was a big business for a while about how do you do this most effectively. They've kind of closed a lot of those loopholes in the meantime, but it sort of is a big business. Typically, though, you don't want to consider self loops because you don't want nodes making themselves kind of. I mean, everyone would do that then, right? And then everyone would just be a little bit more important, and so it wouldn't mean anything. It would just all sort of cancel out, right? So you don't want to do that. The idea of PageRank was you somehow wanted, the entire web to emphasize the importance of different nodes. Now, of course, there are obvious kind of tricks you can play here, like you can set up fake pages that all point to the page that you really want. And in fact, this is exactly what happened for a very long time and still does happen. So that there are all these sort of edge cases, but I think allowing self-loop is something you typically don't want to do. Yeah. Okay, so let's, quick poll now. Okay, so this is actually a multiple choice. More than one thing can happen here. And some of these actually, again, this is a more think about it rather than there's a definite answer here. What would happen if we avoided the step in PageRank of replacing all zero columns with the all one columns? So the options are, and you can select multiple things here. The algorithm would take longer to run before it converged. You wouldn't get kind of a stationary set until a very long time. Pages with no outgoing edges would increase in importance. It's another possibility. Pages with no outgoing edges would decrease in importance. And the sum of all probabilities would no longer, this vector x would no longer sum to 1. So which of those would happen here? Remember, we're saying we just ignore just that one step. So we just don't replace the zeros with all ones. And assume they stay 0. We normalize each one, but just assume they all stay 0. They don't, when you divide by their sum, they don't turn nan, they just stay 0. Okay. Okay. So there's only one actual right answer here. The rest are up to debate. I mean, no. So they aren't wrong, but the rest are all up to debate. So the one thing that definitely happens when you do this is that definitely the probabilities don't sum to 1 anymore, right? Because we have a row of all zeros in our matrix. Whatever weight we sort of had going into that node just vanishes now. So it sort of disappears and nothing happens. The rest now are all kind of debatable, actually. So do they increase or decrease in importance? So one thing that will happen is that I think it will take longer to converge because unlike before, you actually will, the vector x is actually going to be decreasing in size. So you're actually going to keep sort of getting it smaller and smaller. It actually won't really converge. It'll eventually just all go to 0. All the weight will essentially flow into these things that have zero weight. So all your sort of, all your weight converges to this place. However, in the meantime, there's going to be sort of relative importance of these different things, right? So does anyone want to argue actually why it might cause edges with no outgoing nodes to increase or decrease in importance? Yeah. Uh-huh. Okay. So I think it's actually sort of, these two are kind of, I'm not convinced either of these would happen, actually. So the point I want to make here is that the notion of importance does not really have to do with the weight going into an edge, right? The notion of importance is when you sort of take this little walk around the graph, where do you end up? Right? So right now, when I go to a node, or in normal PageRank, when I go to a node that has 0 outgoing edges, I jump to some other random node. Right? I jump to kind of a random node and then pick it at random. In this new model here, I actually would just kind of disappear after that. I kind of, I end the game permanently. So it's not clear to me that you would end up in these nodes any more or less based upon this. I mean, modulo the fact that you're going to end up in everywhere a lot less, period. Right? You just kind of, instead of jumping to somewhere new, you jump to nowhere, which doesn't really necessarily increase or decrease the importance of those nodes. So I would probably say actually neither of these two things happens, but this one and this one do happen. But I think it also has to do with how you. It's very peculiar to sort of what you do with those columns. So for example, if you took a different approach and made all those nodes that ordinarily vanish just link to themselves, so you do allow them to link to themselves, then those nodes would increase in importance then, right? They would sort of keep looping back on themselves, and you would always end up in one of them, so they would be very important in terms of this process. So again, this is just sort of more to kind of get you thinking about the algorithm rather than anything else. But definitely this one does happen, and the others I think would be arguable about whether they happen or not. Okay. Let's go back. Maybe the question should have been actually about the what happens if you link to yourself. That has a more obvious interpretation. I think this one is a little bit maybe ambiguous. Yeah, the question over there? Yeah, we could certainly renormalize. So we're not doing that in PageRank. So that's why, I mean, the PageRank algorithm is just this. So we don't do that. We certainly could renormalize x. So we could take x every time and then renormalize it to be a probability distribution. And then I actually have to think about what would happen. That would actually be a good question about what would happen then. I have to think about what would happen. I feel like nothing would really change, but let me think, because you basically just sort of normally you jump to nowhere, and now you sort of in normalizing to something very similar as jumping to anywhere. But I actually am not sure about that, so I'd have to think about that a little bit. Okay, so let's so that's going to be all for PageRank for now. It's a algorithm that could take a lot of time sort of studying it. If people actually want to think about like tutorial topics, or even projects, one very interesting question is sort of what people have done historically to trick PageRank, and how those defenses have been, or those attacks have been kind of defended against by improving the algorithm. Because there are obvious fixes here, right, that were used by a lot of people doing. Basically trying to bump up the popularity of sort of scam websites. Okay, so let's move on now, and hopefully we will have still time to get to the free text section here, but this is actually much more brief because I'm not going to go through it in as much detail. Are algorithms for community detection. So this is a very common topic in things like social networks. You want to find out who are clusters of friends in a social network. So if I have a graph like this, it's sort of natural to look at this graph, and I've also helped things out by sort of drawing it this way. But if you look here, there are these 3 clusters here that are sort of all kind of tightly connected. In this case, they actually do form a clique. They're actually a fully connected set of nodes here. In those cases, they aren't quite, because there are some. Actually, this one might be too. Is that one? No, there are some that don't have edges between them, like this one and that one. But there's still sort of these communities that kind of are tightly knit in some sense, right? They're sort of groups of friends that are all friends with each other as well, maybe with only a few nodes missing. And then there are only a few links between these different communities. And actually, a lot of social networks do have this structure. So as you would imagine, they're sort of, friends tend to sort of cluster in groups. And then, but one person will have a friend kind of in an outside group. And so then they have this structure, these social networks. So a big question is, how do I find structure like this? And what does this tell me then? How can I use this to analyze the nature of this network? So we're going to cover kind of one version of how you go about finding these communities. But of course, since this algorithm was published now, I think about 15 years ago, there have been a lot of more recent developments and frankly faster algorithms than this. But this is kind of one of the first algorithms that kind of actually really brought this kind of idea onto the scene. So the algorithm we're going to talk about is called the Girvan-Newman algorithm, 2002, so 16 years ago. And it was one of the first methods for, I guess, kind of modern community detection. And here's the basic idea. We're not going to go into this algorithmically because some of these concepts are a little bit hard to actually compute, or they're a little bit involved to compute. But I want to cover kind of the basic ideas. So the idea here is that we're going to partition a network by removing removing edges in the network. And by removing edges, we're going to kind of form subgraphs, separate connected component or separated components of this graph that then kind of become communities in the graph. And actually, we don't ever just sort of form single communities. What we do is we sort of keep removing edges to form kind of this hierarchical structure to the nodes in the graph. And then we eventually kind of cut it at some point to say, at this layer, we're going to say everything below this that are still together after this point is a community. OK, so the way this works is that we're going to actually create kind of a hierarchical breakdown of these nodes. And I'll show you what I mean by that in a second. It'll be more clear when I actually give an example. But what we're going to do is the following. We're going to compute a score for each edge called a betweenness score. What this score captures is it captures the number of shortest paths that pass through this edge. It's kind of a weird idea. But if you think about it, if I have two dense graphs here, right, and then one link between them, every shortest path from graph 1 to, from graph part A to graph part B has to pass through that edge. And so that edge has what's called a high betweenness factor. And so if I want to remove an edge that sort of, is connecting the most sort of disparate regions, I should remove the edge with the highest betweenness factor, and that would only leave my two kind of communities remaining intact. That'll break the graph into subgraphs, and then we'll recursively partition each one according to the same algorithm. Now the challenge here is efficiently computing this betweenness in the graph as we partition it. We're not going to cover that. I'll maybe give a brief illustration of how this works, but we're not going to actually cover how it works. You have to run actually a shortest path algorithm for each like a single source for each node being a source in the network, and kind of accumulate the number of paths you observe along each edge, which takes it's not trivial to do in large graphs, but that's sort of how these things work. Since then, there have been much faster algorithms that sort of apply to this same thing, but I think for historical reasons, it's kind of good to know about this. This is one of the original community detection algorithms. So let's see how this works. Here is a graph with 14 nodes that we want to partition into communities. Okay? And I'm going to start by computing, at least for this initial graph, the betweenness for each vertex. Now, for each edge. Betweenness is an edge property under this algorithm. Now, I'm only going to show it for there's obviously a lot of symmetries here, so I'm only going to show it for the sort of the unique types of edges here. But there are really 4 different edges that matter in this graph, and the rest all have the same ones. So this edge between 8 and 9 has the same betweenness as the edge between 3 and 7, just because it's a symmetric graph. So these are the betweenness scores for the edges in this graph. And take a little bit of time to see, but it's actually not that hard to convince yourself that these are, in fact, the right scores. First of all, between 1 and 2, that's going to be a betweenness score of 1. Because if you think about all the shortest paths, you'll never go from 1 to anything else through 2. Right? Only if you're going from 1 to 2 will the shortest path between those two nodes involve that edge. So that edge between 1 and 2 has a betweenness of 1. Now, the edge between 1 and 3 has a betweenness of 12. And the reason is, if I look kind of at the node 1, if I look at all the other nodes, not 2, but all the others, there's 12 other ones. So the shortest path from node 1 to node 3, node 4, node 5, node 6, and 7, et cetera, up to 14, always goes through that edge. Okay, so it's going to have a betweenness score of 12. And actually, for edges that kind of partition the space like this, is actually not that hard to compute. So The next one's 33. And actually, you can kind of start to see the trick now. So the trick is, if all the nodes are on one side and the other one, then there's 3 nodes on that side and 11 nodes on this side of this thing. And so all 3 of those, to get to all 11 of these, the one has to pass through there. So that between the score is 33. Here you have 7 nodes on this side, 7 nodes on that side. So to get from each of these 7s to each of those 7, you have 49 different paths through. Okay, so it only gets hard when you sort of have multiple directions that can kind of get you through somewhere. But here it's actually pretty straightforward when you have these things that can be partitioned by removing one edge. So how does that work? What does this look like when we kind of break down this graph? Again, I don't want to spend too much time on this because this is not, I'm not going into details about how you compute those scores in the general case. But in this case, where you can compute them kind of easily here, you first remove this one. That's the one with the highest betweenness. Now you have these clusters here. You actually have to recompute the betweenness now. You can't actually save easily your old computations to sort of cache them. You only have to do that when, for the nodes that change. So if I remove, only one of these edges, of course I don't have to recompute everything over here. But let's just go ahead and remove all the ones with the same betweenness score that's sort of next. That would actually remove all of these. And if you do it one more time, you actually would just have an individual nodes in this graph. So the point is, so these incentives are the communities in this graph. It's not whether you want to put 7 in one of these or so. It depends how you remove them. But obviously, all these edges that I removed here have the same betweenness score. And so I'm just going to remove them all at once. And what's left are these kind of communities. But what this really creates, in some sense, is what's called a dendrogram of the graph. So there's actually a hierarchical partitioning of this graph into multiple sort of sub-regions, right? So the first region here is this first kind of split that splits off the ones that were on the left from the ones that were on the right. Once you go beyond that, you split off, the 1, 2, 3, the 4, 5, 6, and the 7 all into 3 separate categories. That's this breakdown. And of course, if you did it, and of course you do the same on the other side. If you did it one more time, you of course would break up, the 1, 2, 3, and the 4, 5, 6 into their own individual, single node communities. So really, what you get when you run Girvan-Newman is you get one of these kind of hierarchical structures over your graph, and then you can choose to kind of cut it at any point to get a sense of where the communities are in your graph. It doesn't actually give you just raw communities. It gives you a breakdown, a hierarchical breakdown like this that you can then use to kind of, depending on how fine-grained you want to be, you can use to find different community partitions of your graph. Okay, I'm not going to go too much farther because that was kind of conceptual. I didn't define, for example, algorithmically how we compute betweenness in the general case. You can imagine it has to do with things like shortest path computations, but I'll leave that for some links in the notes if you want to read it. Okay, so yeah. Yeah, so that's a great question. So the question was, do 7 and 8 exist outside the communities? Right, so this is a little bit ambiguous, right? So if you split at this level, right? If you split at that, if you choose to kind of cut your graph at that level, then these would be your communities. You would just say, I've stopped here. I have 2 communities in this graph. That's what it is. If I go one level beyond and say I want to cut at the next level, now these would be your communities. And I'd have 6 communities here, 2 of which were just single nodes. So it's really a matter of where you choose to split it rather than any fixed definition of what a community really is. And actually, a lot of work in more modern partitioning, community detection algorithms has to do with essentially faster metrics for things like betweenness that you can use to break things down. Because betweenness is actually, it's nice, but it's quite slow to compute. And so people have wanted to speed that up a lot. And I'll say it's a good project or tutorial, for example, would be on things like Louvain community detection and stuff like this, which are a little bit more modern methods for doing similar things. Okay, so let's just finish. And I only have a few slides here, actually, because the main idea is actually pretty straightforward for libraries. But I want to highlight kind of some of the libraries you will use if you want to do graph processing and, and therefore network analysis in Python. And we're going to focus in particular on the NetworkX library. So in the homework, for instance, you start off by implementing, this is the 688 homework, you start off by implementing the graph library in, or you don't implement it, you just check the routines using NetworkX, and then you kind of implement your own version of some of the functions that we've covered here. So NetworkX is a Python interface for constructing graphs, for storing information on the nodes and edges, for querying information about the graph, and for running. It has a pretty large suite of built-in algorithms. So, for example, it has Gervin-Newman, it has Dijkstra shortest path, it has PageRank, and it has many, many others actually that are all kind of in the library of functions that it maintains. Now, it actually does use I forget if I have this here. Yeah, it actually uses internally the dictionary, adjacency dictionary representation for a matrix. So you can look at what it's doing internally. It's using exactly that representation I talked about last lecture, where you have a dictionary of the nodes. Then each one of those points to a dictionary of its adjacent nodes. It's what it uses for representing dictionaries. And just like I talked about too, you can obviously also extract things like adjacency matrices from the adjacency dictionaries. Now, it's not the best thing for really large graphs, though. Remember, it's storing everything as dictionaries in Python. Those are reasonably fast, but if you're talking about web-sized graphs, you're not going to be able to do it with NetworkX. So it's not by any means kind of a industrial strength graph library, but it is pretty good for millions, maybe even tens of millions of nodes, some similar number of edges. It can handle that pretty well just in RAM, so things just kind of work out fine. If you need to handle really billions, trillions of nodes, you can't do it here. Definitely not trillions, probably not billions either. So Google cannot run in NetworkX. They can't run PageRank on NetworkX these days. So let's just see a few. All I want to do is sort of illustrate a few of the commands that you might want to use, and really refer you to NetworkX as this website as the reference for it. So first of all, there are two types of graphs in NetworkX. There are directed and undirected graphs. So the nx.graph, I guess I usually import, again, like all useful libraries, they all have two-letter acronyms. So I import NetworkX as NX. I can create either a graph or a digraph. A digraph is a directed graph. So there are two different classes for graphs and directed graphs, or undirected and directed graphs. And this is really because, from an algorithmic standpoint, there are a lot of algorithms that need one or the other. And you really need to sort of know which type of graph you're operating on to run these algorithms well. So they just decided to split these up into two different types of graphs, different classes. You can call a bunch of functions. So you can call functions to add or remove edges. So if I want to add a bunch of edges, I can just input a list of tuples. Say g.addEdges from a list of tuples here. If the nodes do not exist that these tuples refer to, they will be created, and then an edge between them will be created. So there's sort of one call to create the edges and the nodes in this addEdges call. So actually, all these things I'm talking about are edges, but they will also add the nodes that you need to make the edges. There also are add node calls, but I never actually use those because almost always when you create an edge, when you add a node, you want to add edges to it, and so you can just create the edges, and it'll figure out which edges actually exist or not. This is a call to add edges from a long list. You can also sort of add edges one at a time. You can remove edges. You can also remove edges from a list, and I can also add edges from a list. I guess I'm repeating myself there. I might just do this to put back the graph in its original form here. So this is sort of the most common calls you make when sort of setting up a graph for the first time. The other thing that sort of, and actually if you do want to see kind of the internal representation, those graphs, they are just dictionaries. So the graph here, if I say G with node C, that'll return this adjacency dictionary representation where the values are the adjacent nodes, and then, the keys are the adjacent nodes, and the values here are actually empty dictionaries themselves. In general, actually, NetworkX can represent arbitrary elements on edges, can store kind of arbitrary data on an edge. So that dictionary, if you have a lot of data on this edge, will actually store the data for the edge. But by default, it's only an empty dictionary. People were asking last time about what you put in that on those as the value on those edges, and you can check it out with what NetworkX actually does. Is a question there?
What happens if we remove one node that has edges rather?
Yeah. So the question is, what happens if you remove a node that has edges to other nodes? It will remove all those edges too. Okay, so you have things like a g.nodes function, which will print all the nodes. You have a g.edges function, which sort of iterate over pairs that are edges. This is sort of like, if I want to loop over all my nodes or all my edges, I would call one of these two calls. And then finally, this is the notation here for specifying properties of nodes and values. Of nodes and edges. So if I say node A and then some node property equals something, that actually assigns node property of that node to this thing. Notice I have to make this call .node of A, and the property equals some value. If I say g.edge with the to and from an edge property, I can assign some edge values there. What this is for essentially assigning some data to nodes or edges themselves. In fact, any data, because it's a sort of an arbitrary dictionary, we can assign to nodes and edges. So oftentimes with real graphs, you will want to not just have nodes and edges, you'll want to have some sort of data assigned to the nodes and data assigned to the edges. And the way of doing that in NetworkX is through these calls here, this .node call and the .edge call. It takes a little while to get used to, but this is sort of the main way you assign data to nodes or edges. By default, the nodes call that I had here will not return the data. It will just return the nodes, the actual nodes themselves and the edges themselves. If you want the data, you have to specify that you want data back from these things. Think second to last thing. Any questions with that? Again, I'm going quite fast here, but these actually are the functions that I use most when working with NetworkX, at least setting up graphs, right? It ends up being mainly just a bunch of calls like this and a bunch of calls like this to build your graph. Okay, so the last thing I'll say is that we can draw graphs with Matplotlib, and the default options are extremely ugly here. It's very hard to know what that graph actually is. That actually is our same graph, I believe, that we've been dealing with before. But for some reason, instead of using arrows, it uses these bars. So you have A, B, and C. And so A points to B, B points to C, C points to A, and C points to D. The other thing is that it will sort of pick locations for these things in some way to kind of make the graph most reasonable under 2D. But if you just call .draw, nx.draw, you aren't actually putting in the positions. If you want to have pretty graphs, there are a bunch of tools that help you draw the graphs in a much more pretty way. NetworkX does interface with some of those, so you actually can get much nicer figures out of NetworkX. But for very quick debugging, this can kind of work okay. But just don't include these things in like a paper or a report. They're just awful. They're for your own use on really small graphs, or to get even a sense of what this graph looks like, not to actually try to showcase any information about these graphs, because this thing here compared to this thing that we've been looking at, I mean, that's just much more obvious what's happening than in this graph here. Even though it's the exact same graph and there are 4 nodes in it. Okay, and the last thing I'll say is that all of the algorithms we talked about so far are, of course, implemented in NetworkX. So, shortest path algorithms, PageRank, Girvan-Newman. Girvan-Newman, make sure you're using NetworkX 2.0 for this class. You need that for Girvan-Newman, but they're all there. Okay, it's getting a bit late, so I might just jump to free text because I want to get through that so that we can finish it next time, ideally. So unless there are maybe 1 or 2 questions, I'll just move on. Okay, so let's talk about free text. All right, so let's see. Okay, I want to do this. All right. So we've kind of covered a lot of sort of basic data structures and types that you will see in data science. We've covered relational data, we've covered graph data, we've We covered vectors and matrices. These are kind of the fundamental things you're going to see. But I want to spend a little time now on kind of a slightly different thing, because it's not really structured data in the same way, but it's a data type that is very common that you will, I think actually even more and more, see in practice, which are essentially just raw text data. Now, I could do similar things with like raw image data, but I'm actually going to wait on images until we talk later, much later actually, about deep learning, because image processing in particular has kind of been revolutionized by deep learning to the point where I think even in a data science course you can mention a little bit about deep learning as it relates to images. But free text and very basic NLP is actually, I think, at least the way I'm going to talk about it, is still kind of in the category of kind of basic data processing. It's not really advanced analytics or stuff like this yet. It's sort of just basic models. We will have some probabilistic models. We'll have kind of the things that you can generate like Shakespeare text from, that kind of stuff. But they're pretty basic models, and so I think they're better suited here to this kind of discussion about representations of data and how we store and process data. Okay, so this lecture is actually going to cover, and this one really and next one is going to cover a bunch of topics. I don't think we're even going to get to all the ones for this time around. But it's going to cover first kind of the idea of free text in data science and what this sort of means and kind of where this is, where these techniques are useful and why you might want to use them. Then we'll spend most of our time actually on bag of words and TF-IDF models. That stands for term frequency inverse document frequency. We'll talk then about language models and n-grams, and we'll talk a little bit about word2vec and libraries for handling free text next time. I don't think we're going to get to language models this time, but we'll see how far we get. Okay, oops, those are my announcements. Okay, so let's talk about free text and data science. So a large amount of data in many applications you will see involves kind of raw text, right? People like to generate text. If you're browsing the web, for instance, you will not only have the graph structure of the actual links, the web page links, you also have a lot of text on these web pages, right? And for the most part, that will not be nicely structured like in a relational database, right? Well, as you know, web documents are structured according to HTML, but that's not the kind of structure you actually want to follow in terms of extracting content by any means. As you all know from the homework, even XML is hard enough, and HTML is just much, much worse even. So there's a lot of text out there. This is kind of one of the primary ways humans generate information. And so a big question in data science is kind of, what do you do with this? How do you process and store all this text data when it has obvious meaning to us, but barring the ability to really have a computer understand free text, which is not what we're going to talk about today. What do you do with data like this? Now, there is, of course, a whole field of computational natural language processing, or just NLP, which is really about writing programs, in the case of computational NLP, that can understand natural language, right? So if you've taken a course in sort of natural language processing before, or sort of seen this term before, I guess some people differentiate between natural language understanding and natural language processing, but for the most part, these two things kind of refer to the ability to kind of understand language at a little bit more fundamental level, really as structured information about language, right? And we're not going to do that in this lecture here today. There may be sort of soon coming up in the future, kind of off-the-shelf libraries that can do a good job with this. But right now, we're still kind of a ways away from really having easy ways to understand free text data. And so what we're actually going to do is not try to sort of meaningfully interpret text, but just give you a bunch of tools that will let you extract some information from relatively unstructured text data. So we're going to cover sort of text at a very superficial level in some sense, but that's actually mostly what happens in data science. That's why this lecture is up here, not much further along in terms of the actual modeling techniques that we're going to use. Okay, so to make this point, and this is always the things you do whenever you talk about natural language, is one reason why this is so hard is that unlike say XML, natural language is not well defined. So there are ambiguities in language that cannot be resolved unless you know the context they're actually talking about. So there's a great quote from Groucho Marx that says, while hunting in Africa, I shot an elephant in my pajamas. How he got into my pajamas, I don't know. So obviously that's not how you interpret that first sentence, but you have to know about what he's talking about in order to actually be able to understand that quote. More generally, actually, this is actually a type of a sentence called Winograd schemas. So Winograd schemas are essentially sentences where one change in word will change who the actors are, or like who the people are being referred to in that sentence. So the city councilman refused the demonstrators a permit because they feared violence. If the word there is feared, then the they is referring to the councilman. If it says the city councilman refused the demonstrators a permit because they advocated violence, presumably then they is referring to the demonstrators. So you actually need to know the context of all these words. You know what councilmen are, what advocating is, what fearing is, what a protest is, in order to actually understand how to parse this sentence, how to know what they refers to. And so again, ignoring everything here, the basic point that I want to make is that we use, we could really easily interpret both these sentences if you just saw them without this sort of context here. Maybe you would give it a little second take, but it wouldn't be that hard. When we read language, we impose a huge amount of our contextual knowledge onto that language, right? And it becomes very hard to write a program that can do that. I mean, I think writing a program that can solve these things is still, to a certain amount, kind of an unsolved problem. We are certainly making progress in that direction, but there are still some very hard things that come up when we talk about what sort of natural language actually means, or at least how you would write a program to understand natural language. So we are not going to try to do any of this in this course here. And the reality, and why this is okay in a lot of cases, is that a lot of times, in data science in particular, when you're talking about a lot of data, maybe for the most part kind of unstructured, but not trying to trick you like those Winograd schemas were, we can actually extract a lot of information just by looking at text at a very superficial level. So here are two reviews for a movie. It's for the one of the Star Wars movies. And one of them says it's truly a stunning exercise in the blah, blah, blah. And the other one says it's loud and full of vim, but a little hollow and heartless. And so it's not very hard to sort of, if my question is, is this a positive or negative review of this movie, it's not very hard to sort of latch on some keywords here that are usually pretty good at indicating it. Now, of course, that doesn't always work. Someone could always say this is not a bad movie, right? Meaning it's a good movie, but that's not really how we talk. We usually talk by using the words that we actually mean, and not with qualifiers in front of them to negate their meaning. So we can very often get the overall gist of natural language text without actually understanding it at all, is the basic point that I want to make for natural language processing, or for free text storage and processing in data science. We can get away very often with really superficial types of analysis. And this is going to lead us to sort of the different models for how we actually think about free text in data science. And so again, the point here is that oftentimes in data science, we don't need to really understand the text to sort of solve our ultimate goal. If our goal is to build another prediction system or to classify something about these documents, we can oftentimes do that without actually understanding what they're about, with just taking some very basic kind of keyword analysis of the text and going from there. So if you are Google and you're crawling the entire web, they're trying to do all sorts of understanding now. But if you're trying to crawl the web and you want to understand the general gist of different pages, in addition to their link structure, you can do a pretty good job of just sort of looking at certain keywords that appear in those pages and ignoring all the actual fact that this is an English language document written with whatever context it has. So I'm actually going to discuss three very simple but useful techniques that can be used to infer some meaning and text without a deep understanding of that text. Let me just change that to 3 right now before I forget. We're going to talk about bag of words approaches and TF-IDF matrices. We're going to talk about then n-gram language models, and we'll finally finish by talking about word-to-vec models next time. Now this is sort of a caveat I mentioned here, is that this may be a lecture that changes more than others in the next, say, 5 years. Actually, already this year I decided to add the word-to-vec models from last time because those are already becoming kind of a standard in how you analyze text data. But it could be that within a few years we actually have much more off-the-shelf powerful techniques for analyzing text in a way that preserves more of the understanding of it. So I think, for example, we've gotten there with images. With images, you no longer do things like just take histograms of the image or just histograms of the colors in an image. We have kind of off-the-shelf, more powerful techniques that can actually work with those things. So this whole sort of lecture may change within a few years when we have a simple model that will actually, well, not simple model, but we have a simple library you can download that will actually understand a piece of text for you and be able to answer questions about it and stuff like that. And when we're there, we'll have to move this lecture to a later part, and rewrite it. But that'll be a small price to pay for the fact that we have much better techniques for processing language. Okay, any questions so far? Okay, so let's jump right in to bag of words and TF-IDF approaches. So a brief, quick note on terminology. So in this lecture, I'm going to talk a little about documents, and here documents means just some block of free text, some individual group of free text. So it could be an actual document, it could be a text document, or it could just be a field in some page, right? So document will always just mean some sort of collection of free text. Words or terms refer to individual words, which are tokens separated by white space, and often also refer to things like punctuation. So oftentimes you'll also include a period as a word because it's very common, occurs fairly commonly, and you don't want to have a word followed by a period different from the word itself, right? So you sort of either strip out or include punctuation as individual tokens in your representation of these documents. And finally, corpus refers to a collection of documents. So corpus will refer to a lot of documents, the entire body of documents we're analyzing together. All right, so the bag of words is essentially the cloud view of documents, the word cloud view of documents. So this is a word cloud of the class web page. People have probably seen word clouds before, right? You take all the words in it on some page, and you count the ones that are more frequent than others, and you assemble them. Not you literally. I guess people used to do it manually, but now it's all done by programs. You assemble them into basically a pleasing graphic that includes all the terms or a lot of the terms in proportion to how commonly used they are in that document. And so this is what a bag of words is. The bag of words is we throw away all the entire document, and we just keep the word cloud. Of course, not in like picture form, but the effective data behind this word cloud. What we're going to do is we're going to represent each document as just a vector of word frequencies. The order of the words is irrelevant. All that matters is how often they occur. And that's how we're going to represent our documents. And we call it bag of words, obviously, because it's like you take all the words in the document and throw them into a big bag. And then all that matters is sort of that bag of them, right? It doesn't matter the order of them. You just have a big collection of words in a big bag. That's all that actually matters. And again, this seems like it's a horrible idea, right? Because we are taking all the information we know is important, like the order of words, and throwing it away and saying, yeah, it's good enough just to look at whether a word is there or not, or how many times it occurs in a document. Which again might seem crazy, but the fact is that the fact that we have things like this makes it seem like this might be okay, because I could probably classify whether those two reviews were positive or negative using bag of words, right? If they say magnificent and wonderful and great a lot, it's probably a good review. If they say bad and hollow and heartless, it's probably a bad review. So let's just take a quick example. Here's 3 different documents that relate to this lecture, or weird phrases actually that relate to this lecture, not even full sentences. And I'm going to represent them as bag of words in their bag of words representation. So I'm going to form a big matrix, actually, of all my words here, where each row corresponds to a document, and each column corresponds to a word. And the entry in this matrix here is just the number of times that word occurs in that document. So the first document, in this case, says the goal of this lecture is to explain the basics of free text processing. The second document says the bag of words model is one such approach. And the third document says text processing via bag of words. So obviously there are some words that overlap here, some words that don't. But if I look at all the words, the set of all words that occur in all these documents, I can create a list of all the words. So this is actually not quite all of them, because there are a few more, but this is a good selection of them. The is of goal, lecture, bag, words, via, text, etc. And then there are my 3 documents, each corresponding to a row in my matrix. And the number here is the number of times it occurs. So all documents have the word of. The first one has the word of twice. The second 2 have it just once. But only the first one has the word lecture, for example. The rest don't have it. And each document now is just this vector. It is this vector in the matrix that we're going to use to represent the occurrence and frequency of words. And this is kind of nice in a lot of ways, right? Because as you can imagine, it's much easier to store that big matrix for a whole set of documents than the actual documents themselves, right? If all you have to store is that matrix, you've sort of saved a lot of time, because you don't have to worry about, every time that there's a word that occurs multiple times, you can basically get free storage by just saying, okay, it's just this word of, and it's going to occur this number of times in the different documents. I should also mention that I kind of motivated sparse matrices as one case, or I motivated these examples as one case where sparse matrices come in handy. As you can imagine, if you have a lot of documents, there's going to be a lot of words that only appear in a few of them, right? So there's going to be a very long tail of words. And for that reason, when you get a big collection, this matrix here is often sparse, and you want to store it as a sparse matrix. You do not want to store it densely, or computing all the things that we're going to compute from these things is just going to be way too costly. Okay, is that clear to everyone, the representation we're using here? So that's going to be our entire representation of our corpus, is that matrix X. Okay, now the term frequency refers to just this entry in that matrix. It's referring to the counts of each word in a document. We're going to denote it as TF I, comma J, which is the frequency of word J in document I. Sometimes they're reversed. I'll try to be consistent with this matrix, so I'll try to always refer to the first term I is the document, and J is the word. Now, this term frequency often is just a count, the number of times that word appears in the document. But actually, there are other possibilities as well, and there are different rationales for these different things. It is common to just ignore the actual counts and just have all the entries be 0 or 1 based upon whether the word occurs there or not. So you just ignore the actual count of term frequency. You just say, it's a binary flag saying, does that word exist in this document or not? So all of these terms here that are not 0 will just become 1s. There are also some other interesting things you can do. So what people have found is that sometimes if a word occurs a whole lot, it'll kind of bias this document to kind of, the document becomes too much about that one word. And so you want something kind of in between, but you don't want to just have binary counts either. You want something kind of in between. So a common thing people do is they actually use like a log scaling of words. So they'll actually take the log of 1 plus this thing and call that the term frequency, or a scaled term frequency. Or maybe they'll divide it by the maximum term frequency of all the things in the document to kind of keep them between 0 and 1 in all cases. Okay. So just, again, this is sort of incidental issues, but just know that people do things like this with term frequencies, and they're all still referred to as term frequencies. Okay, so the next thing that I want to mention, and I guess I have 10 more minutes, so hopefully we'll get through all this, is that term frequencies tend to be sort of overloaded on very common words, of course, right? So for example, in this document here, all of them, or a lot of them, include the word the, is, and of, yet those words, of course, don't actually say anything about those documents. Now, those are so common, actually, that oftentimes, we just remove them manually. There's a list of what are called stop words that you just oftentimes throw out entirely because you don't believe the word the really indicates anything about your document or not. Maybe it does, but usually it doesn't, right? So usually you just want to throw that word out. But it's something we don't do that. Even if we do that, there are still probably going to be some words for your particular corpus that occur a lot more than others. And because they occur so often, this is actually a bad thing in some sense, right? Because they occur so often that they become kind of meaningless in terms of differentiating the actual terms in your, or the different documents within your corpus. So if your documents are all about movies and you see the word movie in all of them, that wouldn't normally be a stop word. You wouldn't throw that word out normally. It's not going to be in any library. It's sort of listed as a stop word. But if every single document contains the word movie, it's kind of not that meaningful. So what we do next is we also weight words or terms by something called the inverse document frequency. And what this is so the idea here is if the word occurs very frequently in the corpus, so in a lot of documents, you kind of want to downgrade the importance of that word, right? What you really want to sort of have, as high a weight on as possible are those words that are unique to that document, or maybe some small group of documents. Those are kind of the important words. Those are really the ones that say what those documents are about. And so the idea of inverse document frequency is that you try to, for each word, come up with some measure of sort of how common it is, and then weight the words by the inverse of that. So weighting more highly words that are uncommon and less highly words that are more common. So the most common way of doing this, and again, just like with term frequency, there are other variants. There's all sorts of scalings of this term, is to take for every word. Remember, again, inverse document frequency is not about documents. It's not like term frequency that's about documents and words. It's just about words. So there's only a subscript j here to indicate being over words. So for each word in our entire corpus, right? So for every basically column in this matrix X here, we compute the number of documents that there are divided by the number of documents with word j. Of course, the document, the document frequency would be this one over this one. So the inverse document frequency is this one over this one. And then because that's a little bit harsh to scale it like that, we take the log of that term. And that's the most common definition of the inverse document frequency. It's the log of the total number of documents divided by the number of documents that contain that word. And again, there are more scalings, different scalings, etc., but this log scaling here is the most common. And importantly, note that it is only defined for words, not for word document pairs. So for example, let's take a few of our more common words here, I guess, and some of the uncommon ones. So of here occurs in every single document. So even if we didn't know, to discard of, we probably feel that this word is not very important for differentiating these documents, for telling kind of what's important about each one. And in fact, if you look at the number of documents total is 3, the number of ones that contain that word is 3, and so you have the log of 1, which is just 0. So you actually would downweight that word to have 0 weight. For words that, there are only 3 possibilities here, but for words that occur twice, you actually have the log of 3 over 2, which downweights a little bit because it occurs, more than just once, but not that often. And then the IDF of the goal, the word goal that is, only occurs in one document, so it's the highest of these inverse document frequencies. Now again, remember, this is not the only thing that's going to matter. Also, of course, matters, the documents, the words that do occur in the document. And so what we do really is in this technique, which is really still kind of one of the most common techniques for how we sort of represent documents is that we take the term frequencies and multiply them by the inverse document frequencies. This is called TF-IDF, for term frequency inverse document frequency. So the idea here is that we're just going to take the X matrix, and we're going to replace just the raw counts, just the term frequencies, with their TF-IDF score instead of their raw counts. And this might seem a little bizarre, but all that's happening here is that in practice, most of the properties we want to compute based upon these sort of these sort of representations of these bag of word representations, most of the time, this is sort of an empirical fact, but it's true. Most of the time, most of these facts kind of work better if you use the TF-IDF entries here rather than they're just pure term frequency entries. Right, so it's extremely common. For example, as we're going to see later on in a few lectures from now, if you want to do machine learning over words, it will often help to use TF-IDF scores as kind of a default weighting in some sense for a big matrix like this rather than just using the raw matrix. It tends to work better to use TF-IDF scores as input to a machine learning algorithm rather than the raw inputs. It's a kind of it's just a scaling, but it's a scaling that tends to work well in practice. A lot of things like similarity of documents, which we'll talk about in 1 second, which I have a poll on, but I don't think I'll get to the poll, so maybe I'll just open class next time with a poll. A lot of these things work better with TF-IDF scores than with normal scores. So this brings us to one way of using these scores to compute similarity of documents, which is called cosine similarity. That's actually sounds like a fancy name. Really, it's just a normalized inner product. So you take the TF-IDF scores of the two documents, you take their inner product, and you divide by the norm of the two vectors. That gives you a score that kind of quantifies how similar two documents are. This is most commonly done and most useful, really, with TF-IDF scores rather than with other scores. So it should be obvious that if the two documents are the same, this will equal 1, right? They will be identical. The more terms they have in common, the higher it will be. And if you use TF-IDF scores, then the more kind of uncommon terms they have in common will raise their score, whereas they have a lot of very common words in common, that won't do much to affect their score. So maybe I actually will. No, I have my example here. Okay, the poll is up. You can think about it in the meantime, and we'll start with it. We'll start next class with it. I'll use this example here, but the poll actually basically asks, what happens if you compute cosine similarity with raw term frequencies instead of TF-IDF scores? Do those cosine similarities go up? Do they go down? Or do they about stay the same? Think about that, and we'll start next class with that poll. Okay.